Hello and welcome. My name is Maciej Cieślak and I am an engineer at zBeyond. Today I will be showcasing our product, ePOP Desktop. ePOP stands for Electrified Powertrain Optimization Process and is a core focus of our offering. Electrification is not easy, and finding optimal architectures for project needs is a complicated and long process involving multiple teams. With our product, we enable our customers with powerful insights early on in the concepting phase, allowing them to make meaningful decisions. In today's presentation, I will be exploring the influence of inverter die technology on system performance for a rear-wheel drive vehicle, VW ID.5. We will go through parts setup, requirements analysis, study configuration, and results analysis. At the end of the study, we will determine the optimal solution. The software is delivered with a library of parts. Import of new items into the library is straightforward. As you can see, I've imported 162 files into the data library. Let's see what they are. We've got 7 vehicles, a drive cycle, 36 transmissions, 102 seed motors, e-machines, and 12 different inverters in different technologies. Of course, users are not limited to only those parts. If they wish, they can create new parts according to their own specification. The next step is requirements analysis. We will be inspecting VW ID.5, so we need to choose it from the drop-down list. According to the WLTP cycle, and let's set the minimum velocity of 180 km per hour, peak torque output of 3600 Newton meters at the wheel, and 150 kilowatts of power. Step 5 is adding acceleration requirements. We can add acceleration from 0 to 100 km per hour, and we can set the time target to 10 seconds. As you can see, our actual reported time with these settings is 9.5 seconds, so we are within the target. We can look at different tabs where we can inspect the cycle distribution, cycle breakdown for the WLTP cycle, launch for vehicle speed and vehicle acceleration, and the energies. The next step is setup of the study. We add a new study case. I'll give it a name, VW ID.5. And here we will be inspecting different combinations of the components that we have imported, so that the software will be calculating which combinations are actually meeting the requirements that we have set. So we're interested only in the VW ID.5. And since we are interested in 2 different technologies for the inverter, I will choose 2 inverters with different die technology. I'll choose the Infineon IGBT and the Semicron SiC inverter. I'll leave all the inverters, all the motors and transmissions checked, so they will all be inspected in the study cases. And then we can hit calculate study combinations. As we can see, the software says that there are 7,488 total combinations, and now it's checking which combinations are successful and which are failing to meet our preset requirements. All the combinations have been calculated, and we can inspect the number of combinations in the combinations tab, which will show us which have failed and which have successfully passed. And in the output speed versus output torque graph, we can see all the motors that have been in the study case. Now we can add some vehicle filters to the results. So in our requirements, I have set that the top velocity should be 180 kilometers per hour. So let's set between 160 and 200 kilometers per hour as the filter. And we want 3600 Newton meters of torque. So I can set it to between 3000 and 4500. And then we recalculate the study cases to meet the requirements of these two filters. In here, visually on this graph, we can see which subset of combinations meets our requirements. And in summary, we see that there are 904 combinations of components that meet the requirements that we have set. Next step is to go into the study case and run the study. Running that many combinations have taken a bit of time, and in the meantime I have opened the ePOP viewer, which is our proprietary viewer of results data generated with ePOP desktop. After loading the data in, this is what it looks like. And now I will proceed to set up the viewer to answer the original problem, which inverter will actually minimize the total cost of ownership. These are the results that have been generated with ePOP desktop. And I have preset the x-axis to have the total cost of ownership estimate in dollars, and the powertrain cost estimate also in dollars on the y-axis. What we can see, I've set up some filters. We've got the Infineon inverter manufacturer and the Semicron, which is the SiC. And we can inspect each of the results by clicking on the result, and that opens the properties of all the calculated data. Now, if we were to investigate further to see to be able to meet our requirements, we need to set some filters. So as you remember, our speed in the requirements was 150 kilometers per hour. So we can set it from 140 to 160, and wheel torque was 3500 Newton meters. So I'll set it from 3450 to 3550. As you can see, that limits the number of possible combinations. And now if we filter by the manufacturer of the inverter, we can answer the question which combinations have lowest total cost of ownership. So as you can see, for this inverter, the total cost of ownership estimate is $26,000, whereas for the inverter with the SiC technology, total cost of ownership is lower, $6,370, even though the powertrain cost estimate is higher. We can also inspect further data that was calculated during the simulation. So we can look at the specification of our components. We can look at the residency plots, performance graphs, vehicle speed versus time, and the output torque profile of the combination. So using ePOP desktop, we are able to answer all these questions very quickly and efficiently. ePOP desktop allows us to investigate multiple combinations and make decisions quickly at a very early stage in prototyping phase. Thank you for your attention.